In July 2022, the James Webb Space Telescope turned its mirrors toward a tiny patch of empty sky. A patch so small it would be covered by a grain of sand held at arm's length. A patch that to the naked eye contains nothing, just darkness. What it found there should not exist, not according to our best models of how the universe works, not according to decades of careful theory built by thousands of the brightest minds in the history of science, not according to anything we thought we understood about how galaxies form, how stars ignite, how structure emerges from chaos. What James Webb found in that grain of sand-sized patch of darkness were galaxies, thousands of them, ancient ones, massive ones, fully formed ones, galaxies that according to everything we know had absolutely no right to be there. And the moment astronomers saw them, really understood what they were looking at, the reaction was not excitement. It was confusion, then disbelief, then something that does not happen often in modern science, genuine alarm. Because what James Webb had found was not just unexpected, it was impossible. The images released on July 12, 2022 were immediately historic. The first deep field image from Webb, showing thousands of galaxies in that grain of sand-sized patch of sky, was described by NASA Administrator Bill Nelson as the deepest and sharpest infrared image of the distant universe ever taken. He was right, but the significance of what was in that image went far beyond its technical achievement. As astronomers began analyzing the data, as they measured the light from individual galaxies, calculated their distances, determined how far back in time they were seeing, something started to feel wrong. The galaxies were too bright, not slightly too bright, dramatically, inexplicably too bright for how early in cosmic history they appeared. Some of them were shining with the light of hundreds of billions of stars, mature stars, old stars, stars that had been burning long enough to grow old, in a universe that was barely a few 100 million years old. Astronomer Garth Illingworth at the University of California, Santa Cruz, one of the scientists who had spent decades helping to design and advocate for Webb, looked at the data and said these galaxies were mind-blowing. That is a direct quote from one of the architects of the most powerful space telescope ever built. Mind-blowing. Not exciting, not surprising. Mind-blowing. The galaxies had names now. JADES-GS-Z13-0. A galaxy so distant it existed when the universe was only 320 million years old, Maisie's galaxy, named after the daughter of astronomer Stephen Finkelstein at the University of Texas at Austin, who discovered it in the first few days of analyzing Webb data. A galaxy seen as it was approximately 390 million years after the Big Bang, and others, dozens of others, each one sitting further back in time than anything Hubble had ever clearly seen. Each one more massive, more structured, more complete than any model had predicted. The universe was only a few 100 million years old when these galaxies existed, and they looked like adults. To understand why this is so shocking, you need to understand what we thought we knew, what we were absolutely certain we knew. The standard model of cosmic evolution is called Lambda-CDM, lambda for the cosmological constant, dark energy. CDM for cold, dark matter. It is the most precisely tested cosmological model in history, supported by decades of observations, confirmed by measurements from multiple independent sources, refined by generations of theorists and observers working together. According to Lambda-CDM, the story of the universe goes like this. 13.8 billion years ago, the universe began in the Big Bang. For the first few 100,000 years, the universe was a hot, dense plasma, too hot for atoms to form, too bright for light to travel freely. Then it cooled enough for electrons and protons to combine into hydrogen atoms for the first time. Light streamed free. The universe became transparent. This is the light we still see today as the cosmic microwave background, the oldest light in the universe, the afterglow of the Big Bang itself. But there were no stars yet, no galaxies, no structure, just a nearly uniform sea of hydrogen and helium gas drifting in the darkness. This period is called the Cosmic Dark Ages. Slowly, very slowly, gravity began to do its work. Tiny density fluctuations in that early gas began to attract more gas. Dark matter halos formed first, invisible gravitational wells into which ordinary matter fell. After hundreds of millions of years, and the models say roughly 200 to 400 million years after the Big Bang, the first stars began to ignite. Small stars initially, primitive stars, stars forming in small clumps of gas and dark matter. These early structures grew by merging with each other, small clumps combining into larger clumps becoming proto-galaxies, proto-galaxies merging into galaxies. This process is called hierarchical assembly. It is slow. It is gradual. It takes billions of years to build something as massive as the Milky Way. When astronomers planned the observations James Webb would make of the early universe, they knew what they expected to see. Small galaxies, primitive galaxies, young galaxies still in the early stages of pulling themselves together. The theoretical prediction was clear. In the universe's first billion years, especially in the first 500 million years, you should see the building blocks, the foundations, the early sketches of what would eventually become the grand structures we see around us today. What you absolutely should not see is a finished skyscraper where only the foundations should have been laid, but that is exactly what Webb found. JWST-GS-Z 13-0 is not a primitive proto-galaxy. It is a structured, star-filled, fully assembled galaxy containing hundreds of millions of stars, existing when the universe was 320 million years old. 320 million years. In cosmic terms, that is nothing. The universe had barely started. The first stars should have only just begun to ignite. The building blocks of galaxies should barely have begun to form. And yet here was JADES-GS-Z 13-0, already assembled, already shining, already containing the stellar mass of a significant galaxy. In 2023, a team led by Ivo Labbé at Swinburne University of Technology published a paper in the journal Nature that laid out the full scale of the problem. They analyzed a sample of galaxies Webb had found in the early universe and calculated their stellar masses. The result was extraordinary. Some of these galaxies were so massive, so full of stars, that if you added up all the stellar mass Lambda-CDM predicted should exist in the entire observable universe at that early epoch, these few galaxies alone accounted for a significant fraction of it. Labbé and his team wrote that these galaxies were impossibly massive. That phrase, impossibly massive, became the one that circulated through the astronomical community in the months that followed. Because it captured the problem precisely. The universe apparently made more stars than it had material to make. Or our models are wrong. One of those two things has to be true, and neither of them is a comfortable conclusion. Paola Santini at the National Institute of Astrophysics in Rome was among the scientists who described the findings as a challenge to the standard model that could not be easily dismissed. Garth Illingworth, looking at the data from the JD survey, the James Webb Advanced Deep Extragalactic Survey, noted that the tension between observations and theoretical predictions was real, significant, and not going away. These were not junior scientists making bold claims for attention. These were the people who built and planned the telescope making the observations. And they were telling us something was deeply wrong. 3 explanations have emerged from the scientific community to try to account for what Webb is finding. They are not equally popular. They are not equally radical. But none of them has been confirmed, and the debate between them is ongoing, serious, and unresolved. The first explanation is measurement error. This is the most conservative position, and in science, the conservative position is usually where you start. Some scientists argue that the redshift measurements placing these galaxies so early in cosmic history could be systematically biased. Redshift is how we measure cosmic distances and look-back times. The further away a galaxy is, the faster it is receding from us due to the expansion of the universe, and the more its light is stretched toward the red end of the spectrum. Measure the redshift accurately, and you know how far away it is and how long ago its light was emitted. But measuring redshift for extremely distant, extremely faint galaxies is technically difficult. Some scientists have pointed out that active galactic nuclei, supermassive black holes actively consuming material at the centers of some galaxies, emit enormous amounts of light that could be contaminating the measurements. If the brightness we are measuring is partly coming from a quasar at the galaxy's center rather than purely from stars, then our estimates of stellar mass could be significantly inflated. A galaxy that appears to contain hundreds of billions of solar masses of stars might actually contain far fewer if some of that light is coming from a feeding black hole rather than stars. This is a legitimate concern, and it is being actively investigated. NIR-SPEC, Webb's near-infrared spectrograph, has been taking detailed spectra of these early galaxies to try to separate stellar light from quasar light. The results are mixed. Some of the apparently impossible galaxies do show signs of active galactic nuclei that could be inflating their apparent masses, but not all of them. Several of the most massive candidates show spectra that appear to be dominated by stellar light, not quasar contamination. So measurement error may explain some of what we are seeing. It almost certainly does not explain all of it. The second explanation is that star formation in the early universe was dramatically more efficient than anything we see today. In the universe as we observe it now, and as far back as Hubble could see, star formation is an inefficient process. When a cloud of gas collapses under its own gravity to form stars, only about 10 to 20% of the available gas actually ends up in stars. The rest is blown away by stellar winds, radiation pressure, and supernova explosions. This 10 to 20% efficiency is baked into every galaxy formation model we have. It is one of the key parameters in Lambda-CDM. But what if the early universe was different? The gas in the early universe was denser, more concentrated, composed almost entirely of hydrogen and helium without the heavier elements that form in later generations of stars. Some theorists have proposed that under these early conditions, before the universe had been seeded with the heavier elements that modern stars produce, gas clouds may have been able to collapse more efficiently. Star formation efficiency of 50, 60, even close to 100% rather than the 10 to 20% we see today. If that is true, if the early universe could convert nearly all its available gas into stars, then the impossibly massive galaxies become significantly more plausible. The stars did not have to come from nowhere. They just had to form much faster than we assumed they could. Research supporting this idea has been published by several groups attempting to model what early universe star formation might look like under different physical conditions. The models can be made to work, but they require conditions that are themselves poorly understood, and they require star formation rates far outside anything we have directly observed. This explanation is possible. It may even be partly correct. But it stretches our models in ways that make many cosmologists are uncomfortable. The third explanation is the most radical, and it is the one that a growing number of theorists are reluctantly beginning to take seriously. Lambda-CDM is wrong, not wrong in a minor way, not wrong about details, wrong in a fundamental way about the early universe, about how structure forms, how fast dark matter halos assemble, how quickly the conditions for galaxy formation emerge after the Big Bang. This possibility was already being discussed before Webb launched because of something called the Hubble Tension. For years now, two independent methods of measuring the expansion rate of the universe have been giving different answers. The discrepancy is small in absolute terms, but it is statistically significant, and it has refused to go away despite enormous efforts to find measurement errors that could explain it. Some theorists believe the Hubble tension is pointing to new physics, modifications to Lambda-CDM that change how the universe behaved in its earliest moments. And now Webb is adding a second major anomaly on top of the first. Two independent challenges to the standard model. From two independent observational methods, both are pointing in the same direction, both suggesting that the early universe was more structured, more active, more productive than Lambda-CDM predicts. Scientists, including Alison Kirkpatrick at the University of Kansas, have said publicly that they are losing sleep over this, that the Webb findings represent a genuine crisis for the standard cosmological model. That word, crisis, is not used lightly in science. It means something specific. It means the gap between observation and theory has grown large enough that the theory may need not just refinement, but fundamental revision. We are not there yet. The data is still being analyzed. The debate is still ongoing, but the possibility that Lambda-CDM needs to be rebuilt from the ground up is being discussed seriously by serious scientists for the first time in a generation, and the findings keep coming. This is not a problem that peaked in 2022 and is now being quietly resolved. It is getting stranger with every new observation. In 2024, the Cosmic Gems arc was discovered, a gravitationally lensed system of galaxies seen as they were less than 500 million years after the Big Bang, showing star clusters so dense and so massive they challenge models of stellar physics as well as galaxy formation models. The JD's survey, which stands for JWST Advanced Deep Extragalactic Survey, has continued to push the boundaries of how early in cosmic history we can detect structured galaxies. Each new data release from the JD's team at institutions including the Space Telescope Science Institute, the University of Cambridge, and the Max Planck Institute for Astronomy has found more objects that strain the predictions of Lambda-CDM. The CEERS survey, the Cosmic Evolution Early Release Science Survey, led by Stephen Finkelstein at the University of Texas at Austin, has independently confirmed that the abundance of bright galaxies in the early universe is higher than models predict. Not marginally higher, significantly higher. And the redshift record, the most distant confirmed galaxy ever observed, has been broken multiple times since Webb began operations. Each new record holder pushes galaxy formation earlier and earlier in cosmic history, each one tightening the constraints on what our models need to explain. The universe is not making this easier. It is making it harder. Step back for a moment and consider the full weight of what this means. James Webb was built to answer specific questions about the early universe. Questions we thought we knew how to ask and had reasonable expectations of answering. How did the first stars form? How did the first galaxies assemble? What did the universe look like in its earliest billion years? Instead of answers, Webb has given us a deeper and more disturbing set of questions. Either our measurements are systematically wrong in ways we have not yet identified, which would represent a significant failure of observational technique despite decades of careful calibration, or stars formed in the early universe at rates and efficiencies so far beyond what we observe today that our models of star formation need to be fundamentally revised, or the standard cosmological model, Lambda-CDM, the framework that has guided our understanding of the universe for 30 years, is incomplete or incorrect at the scales and timescales that Webb is now probing. All three possibilities are extraordinary. None of them is a minor adjustment. The Nancy Grace Roman Space Telescope, currently planned for launch in the late 2020s, will survey far larger areas of sky than Webb can cover, giving us statistical samples large enough to test whether these massive early galaxies are as common as they appear to be in Webb's deep fields. The Euclid telescope launched in 2023 is mapping the large-scale structure of the universe with unprecedented precision, data that will help constrain the parameters of Lambda-CDM and reveal whether modifications to the standard model are needed. More Webb observations are scheduled. More JWST data is coming. NIR-spec spectra for hundreds of early universe galaxies are being analyzed right now in laboratories around the world. The answer, or something approaching an answer, is coming. It may take years. It may require new telescopes not yet built. It may require theoretical breakthroughs not yet imagined. But it is coming. In the history of science, the moments that matter most are rarely the moments when a theory is confirmed. They are the moments when an observation refuses to fit the theory. When the data looks back at the model and says, no, not quite. Try again. Copernicus did not confirm what everyone already believed. He showed that what everyone believed was wrong. Einstein did not refine Newtonian gravity. He replaced it. The discovery of the cosmic microwave background did not just confirm the Big Bang. It ended decades of debate about whether the Big Bang had happened at all. James Webb may be giving us one of those moments, not a refinement, a revolution. We do not know yet. The data is still coming in. The theories are still being tested. The debate is still very much alive. But here is what we do know. When the most powerful space telescope ever built by human hands turns its mirrors toward the early universe, the universe that our best models have spent decades describing, and finds something that breaks those models, that is not a failure. That is exactly what revolutionary science it looks like from the inside. The universe has always been stranger than we imagined. More structured, more active, more productive, more surprising. James Webb was built to see further than any telescope before it. And what it is showing us is that the further we see, the more we realize we do not yet understand. The early universe is not the quiet, primitive, slowly assembling place we thought it was. It was busy, it was productive. It was building things we did not think it had time to build. And somewhere in the gap between what we expected and what we found, between the model and the observation, between the prediction and the data, the next revolution in cosmology is waiting to be born. We are living through the most exciting period in the history of observational astronomy, and we are only just beginning to understand what James Webb is trying to tell us.